Hi class, we are going to talk today about applications of the inner product. We have a few applications, really three, kind of two. They both revolve around some sort of regression, okay? Some sort of curve fitting basically. So we're going to talk about orthonormal bases and how they're used in the spaces that are necessary in order to do X, Y, or Z, right? So let's go ahead and get started with chapter 10.3 of our textbook. So let's start off with the theorem, all right? Let S, capital S here, be a finite dimensional subspace. So it has a dimension of M or N, right? It's not an infinite subspace of an inner product space V. So remember, inner product space means that V is a vector space that has a defined inner product, okay? And the inner product satisfies the 5 conditions that we had for an inner product space, right? And suppose that we have a vector V that is in this inner product space, then the closest vector that is in this subspace to this given vector that we have in our inner product space is given by the projection of that vector in our inner product space onto the subspace. Okay, so just to re-emphasize, S is a subspace of an inner product space. This vector V is in V, and the closest vector that is in S to V is the projection of V onto that vector S. Onto that subspace S, right? So what that means is that the distance between V and the projection of V onto S is always less than or equal to V minus S. Here S is any vector in the subspace S, and the only time that this is actually equal to each other is if S is the projection itself, right? Because obviously if S is equal to the projection of V onto S, then these two things are the same and it is equivalent, okay? So you're probably like, Professor Williams, this makes absolutely no sense to me. That's fine because, hey, we have an image to help this out, right? So here I took this from a different textbook, so the values we have here are a little bit different. Here, instead of V, we have B. Okay, so let's say that this whole space is our inner product space. Okay, this column space of A here, which we'll talk about later, this is my subspace S, right? So you can think about it as a plane in 3 dimensions, just for posterity for this example, okay? So if B is in my vector space, my inner product space, the closest vector that's going to lie in this plane is the projection of this vector onto that plane, right? And of course, we're going to extend this to any sort of dimensional space, not just 3 space and 2 space. But that's the way that it works, right? So the closest vector that is in my subspace is the projection of the vector that I'm looking at onto that subspace. Okay, so that's what this theorem is saying. And that should make sense. So let's look at any other vector that would be in this plane. If I had a vector that went this way in the plane, its distance is further away than just basically the shadow that would be cast down orthogonal to the plane, right? So we're looking for basically the orthogonal shadow, the projection of this vector onto that subspace. That's the closest vector in this subspace to our given vector. Okay? And now that that idea is clear, let's talk about this notation a little bit because we are actually going to flesh this notation out a little bit more. Here, A is the matrix that's given for my transformation or for my, like I said before, we're going to be doing some least squares here. So this is just the matrix that I form myself, okay? The column space of this matrix is a subspace of my inner product space. So the column space of A, that is my subspace S, okay? So this subspace is just the space that is spanned by my columns of my matrix I'm going to use. And so my vector that I'm interested in, right, the one that I'm interested in is this one. So this is the one that's close enough, so I need to project this onto my subspace. And my subspace is the column space that's formed by my matrix I'm going to use. Okay, so let's move forward, and then we'll kind of revisit this in a couple minutes. Okay, so now let's talk about weighted least squares. Right, so weighted least squares is used when we want to find the equation of best fit, just like we did in section 8.5. But here, certain data may carry more weight or more emphasis than other data values. Okay, for instance, outliers should carry very little weight in a data set. Okay, they're generally not very representative of what it is that we're trying to portray. In 8.5, we use the standard least squares. We may have tried to fit a line, we may have tried to fit a cubic, or some other function. So right now we're going to really focus on linear regression using least squares, right? So if everything is weighted evenly, then what we had, and this is from section 8.5, we had y hat was equal to c1x plus c naught. So c naught is the constant. This is the coefficient for, or the slope for my variable portion, right? So y hat here is our line of best fit, okay? C1 and C naught were the coefficients that gave me the line of best fit. So for each data value that we have, xi, yi, we have yi hat is equal to C1 xi plus C naught, okay? Where here C1 and C naught, they minimize the distance from our standard function to our line of least fit, okay? So here the distance between the actual output value and the output value that I get from my least squares line, squared plus so forth, and this is for each data value, is what I want to minimize. Okay, so if we do a weighted regression line, then we would basically want to minimize this, but weighted on each sort of difference that I have here, right? So it's a sum of square differences. So each difference squared would need to be weighted depending on what point it is that I'm looking at, right? Because again, certain data values will carry more emphasis than others, right? So maybe my first data point weighs more heavily than my second data point, okay? And so forth and so forth. So the T1, T2, T up to Tn, Ti, I would say, they all have different weights, okay? So again, those weights are positive, right? So here I would let the y1, y2 up through yn be my vector y, and this y1 hat, y2 hat up to yn hat would be my y hat vector, okay? So again, these are my actual data values, right, that come from my given set of data. These are the values that I get from my regression line that I'm using here, okay, where I have the C1 and C naught that minimizes this weighted difference squared, okay? Then we have the following, y1 minus y hat squared plus y2 minus y2 squared. The difference squares here is equal to the norm squared of y minus the y hat vectors, okay? So here, the norm is with respect to the weighted dot product, okay? So here we have just a standard norm, but again, if I were to put the weighted norm, it would be a little bit different. So here, our weighted dot product is, if I have the inner product U with V, it's U transpose times D, where D is a diagonal matrix, where its entries are the weights times the vector V. So we've seen this two different ways. In this video, I'll be using this notation rather than the standard notation that we're used to, just for posterity, so it's very clear what's happening here. However, I will go back and forth between the notation a little bit, which is fine because we really only use it on this example for right now. Okay. So here again, D is the diagonal matrix where everything is 0 except for the main diagonal, where the main diagonal has the weights that we are interested in for each data point, okay? And since y hat equals c1x plus c naught for every data value, we get a equals the following, right? So again, c naught, it's always c naught here, Okay, there's no variable, there's nothing changing here. So I always have constant value here because it's always C0 and then C1 times whatever the x1 value is. And then C0 plus whatever data value I have for x2, right? So if I'm plugging in values here, I always have some constant plus a input value that's changing and then an output that I get from my regression line. Okay, so again, this is really review from 8.5. If you're like, Professor Williams, I don't remember any of this, go to the 8.5 video or the write-up document and just have a review. Okay, so again, since this is the constant column, C0 is the one that will have to show up first, and since this is the variable column, C1 attached with the variable is the one that has to come second. Okay, now if I were to switch these columns around, I would have to switch my data values around. So then this would be C0 plus C1x, and then it might match up a little bit better with my notation here. But just make sure that your columns correspond with your coefficients in your X matrix. Okay. So now you might be saying, well, Professor Williams, if this is my A matrix and this is my X vector, how come the X's are here and there's no X's here? Well, C1 and C0 are unknown. These are the things that I'm trying to find, right? So if we come back a little bit, okay, that's the A times X here, where X is what I'm trying to find. Okay, and column space of A is that subspace S that I'm looking at. Okay, so here we use that y hat vector here, okay, because that's my outputs that I'm going to get every time I plug this in, and I'm going to get A times X, right, and that's equivalent to what I have here, right? So the solution of this is y hat equals the projection of that y vector from here, right, from the data points onto S, where S is the column space of A, right? So again, see the previous image, so it might make this make a little more sense. So this is the V that I have. This is my subspace. I'm trying to project this onto my subspace because that's the closest vector that I have to what I actually need. It's going to minimize it. It's the smallest one that's compatible in this case, right? So let's come here. Right, so this y hat from this regression line is the vector that I'm trying to find. This is in that subspace. It's in the column space of A, where this is coming from this equation, right? So I need the C0 and C1 here in order to find this answer, right? That's what I'm trying to do. So let's do an example, okay? So we want to find the weighted least squares line for the data set -2, -2, -1, 0, 1, 3, 2, 6. Okay, with 2 points weighted 3 times as much as the outer 2 points. So these 2 points are 3 times as heavy as these 2 outer points. Okay, so there's more emphasis on these values than on these values. Okay, for whatever reason. Sometimes this comes up application-wise. There's many applications of this, but it can also come up, for instance, if me personally, I have definitely done this when I'm trying to find a mean value of a grade distribution. Maybe I plot a whole class's final grade versus their homework grade, for instance, and I'll have a whole bunch of values, and the least square line gives me basically the projection of where the class did on average, right? So where the distribution kind of should lay center mass. Okay, so that's one instance where I use this very commonly to assess how my classes are doing. Right, there's many applications. So least square generally comes up in statistics and probability courses, right? So here, this t vector is coming from my weights, right? This is the outer 2 data points, and the inner 2 data points are 3 times as emphasized as the outer 2 points, right? Here my A is all 1, 1, 1, 1, and then this is my X values, right? -2, -1, 1, and 2. Right? My y is the outputs that went along with this. So -2, -2 was a point, -1, 0 was a point, 1, 3 was a point, 2, and 6 was the other point. Right? So my y vector, my A matrix. I'm not going to actually use this t vector, but it's nice to say, oh, this is what the weights are. Okay. Depending on how you want to use the weighted inner product, you could use this vector to help you with your what you need to do. Okay. So notice again that A is A1, A2. Right. This is my vector A1. This is my column vector A2. S is the subspace that is spanned by this. We are using inner products here. Okay, so I need my, I have an inner product space, right? So that means my inner product space should have an orthogonal basis, right? So that's what I want to check here. I want to check to make sure that my A1 and A2 are orthogonal to each other. So if I take their inner product, and again, this is the weighted inner product. So I have 1, 1, 1, 1, okay, times that that weighted matrix, right? So zeros everywhere except for the main diagonal. And then I have my A2. If I multiply these together, right? So if I do this multiplication first, I'm basically multiplying 1 times 3 times 3 times 1, right? Multiply those together and I get out 0. So that means that A1 and A2 are orthogonal to each other, which means that S equaling the column space, the space spanned by these column vectors, is a subspace that's formed by an orthogonal basis. And since it is formed by an orthogonal basis, I can use this subspace for all of my inner product projections. Okay, so therefore y hat is equal to this projection because it is in an inner product space. Okay, so this projection is going to be just a projection of its components, right? So inner product A1y over the norm of A times A1, same thing with A2, right? So this is just our formula of projection of a vector onto a subspace. And so I just need to find all these pieces. That's basically what we're going to do right now for the rest of the slide, is just find these things with respect to that weighted inner product that we have, so that we can just kind of throw them all together into the places where they need to go, right? Substitute them in. So here, the inner product of A1 with Y with that weighted inner product. So again, the other way to do this would just be 1 times -2 times 1 plus 1 times 3 times 0 plus 1 times 3 times 3 plus 1 times 1 times 6. Right? That's the easier way to do it without writing out the vectors and the diagonal matrix. That's the way that we really learn the weighted inner product. Again, as I said before, I'm just going to use this matrix and vector form so that you guys are familiar with understanding that's the same thing. Okay, so again, 1 times 1 times -2, right? 1 times 3 times 0, 1 times 3 times 3, 1 times 1 times 6, right? So it's very easy to calculate these things. Add them all together because it's an inner product, right? It's like a dot product, but it's an inner product. And we get 13. Okay, I'll do this with A11 so I can get the denominator here, which will help normalize this vector on the projection. So again, 1 times 1 times 1, 1 times 3 times 1, 1 times 3 times 1, 1 times 1 times 1, right? So you get 1 plus 3 plus 3 plus 1, and that's 8. And then I'll do this with A2, okay? So -2 times -2 plus 0 plus 9 plus 12, right? 2, 1, and 6 is 12. Add those together, I got 25, right? So 13, 8, and 25. So before I move on to the next slide, just notice that this is going to be 13 over 8 times 1, 1, 1, 1, right? And then this is going to be 25 over what I'm going to get next times -2, -1, 1, 2, right? So we're just plugging our stuff in. Here I just went straight for the form you guys probably use, where I have my weights, right? And then my inner product with itself, right? So -2 squared, -1 squared, 1 squared, 2 squared. So that gives me 14. So I'm going to plug everything in. 13 over 8 times this column vector plus 25 over 14 times this column vector. Okay, and notice that that is my solution, right? So that means, okay, that this is y hat equals ax, because what is a? A is a1 times a2. What is x? X was c0 and c1. Okay. All right. So that means that my c0 is the 2514 and c1 was 13.8. Right? C1 and c0. So real quick, let's do a quick abracadabra and boom. Right? So we're in the land of Desmos now, so we can play around a little bit. I have my data values. Okay. -2, -2, -1, 0, 1, 3, 2, 6. So if we look at what the standard least squares solution would have been, this would have been my standard least squares line, right? This is without the weights. So remember that the inner two weights had more emphasis than the outer two. They're pretty linear already, so it'll be a very, very small change. But if these weigh heavier than these two, okay, then that means that my weighted line should put more of a connection between these two. So you see how it's a little off. This one runs through this point, but there's a difference here. So it should be closer of a line between these two and less so with emphasis on the ends, right? So my weighted least squares is here, right? So as you can see, the blue line is a bit closer to these lines and is a bit further off from the end lines, right? So that the weights are emphasized in the center. Okay, and we're back. So here we have our same graph, right? So that when you see this picture in the write-up, that's where this came from. Okay, so now you know which line is from the standard regression, and then the bottom line here is from the weighted regression. So you see it changes it slightly. Obviously, we have more data points or a different emphasis even. You would see a greater change in the disparity between the two lines. Okay, so now let's talk about Fourier approximations. So this is very similar to what we're doing. We still need an inner product space. However, we're not doing a weighted regression and it is not a linear regression. Okay, Fourier approximations, Fourier series are very, 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 very important. After this video, I have a 3 blue 1 brown video for you that talks more in depth about them and some of their uses. But in industry, it is very, very important. So if any of you are aspiring to be engineers or physicists, this is definitely something you will learn later on. To be honest, a lot of times this is an entire course. If you take a differential equations course, generally you won't see this until you start to do the PDEs, the partial differential equations, but pretty much all PDEs are solved with Fourier series, right? So these are very, very important. We're not going to get super deep into them, but we will touch on the basics in this video. Okay, let's go ahead and get started. Start with the theorem, right? So let the vector space V exist over the smooth space that extends from -pi to pi, right? So remember, smooth means that you are continuous and differentiable. Okay, so there's no value here, right? So you have to be at least differentiable once and continuous, right? So your derivative has to be continuous as well. And let this be an inner product space. So again, it's a vector space with an inner product defined, and that inner product from -pi to pi here is going to be this integral. Okay, so you've seen us use this quite a bit already. And again, the reason for that is because it's an important integral. It's very, very important in applications. Okay, so our inner product here from f to g is given by 1 over pi from -pi to pi of f of x times g of x integrated with respect to x. Okay, so here each integer that is 1 or larger, we have the set 1 cosine x, cosine 2 of x, continuing to increase by an integer amount until n, and then we do the same thing for sine, is going to form our basis for our orthogonal inner product space of V. Okay, so let F sub n be the subspace of V that is spanned by this set. Okay, then for every F, right, every function that is in this inner product space, the best approximation in this space that is spanned by this orthogonal set, okay, is Fn of x equals to projection of that function onto this basis, right, this orthogonal basis. So same exact thing that we're doing before. It's just that my space here is given by this set of functions, right? So this would be similar to my column space of A in this case, right? And the function that I'm interested in, the best approximation is that function being projected onto this orthogonal basis for the subspace Fn. This is given by A naught plus, so again, these are my coefficients, A all the way to An across the cosines, and then we use B all the way to N for the sine, since the cosines go up by 1 and the sines go up by 1. Here the cosine is associated with the A naught term. I'm sorry, the constant is associated with A naught on the cosine side. And you can think of that because this is an odd function, whereas this would be an even function, right? So this is my projection, okay? Here, Fn of x is the nth order Fourier approximation of f, right? So again, we're really doing the exact same thing we did before. It's just that my projection, or my inner product, is given by this, okay, by this function, and my projection, my basis here, is given by this for my subspace. Whereas before we were using the exact same thing, okay, but I had this as my inner product for the weighted least squares example, and my column space was given by the my subspace was given by the column space of this matrix that I had by plugging in my data points to this thing. Okay, so we will kind of revisit that same sort of idea, but this is a little bit different in that my basis is given to me. It's not formed from a matrix from me plugging stuff in, okay, because I don't really know what the function is yet. So here we go, we're here, right? So each A sub k, each one of these, starting from when, so all the ones that are associated with the cosine function, okay, so these are my, like my C0 and my C1 in my last example, so it'll be given by the inner product of that function with its basis function divided by the norm of that function, right? So again, this is all very, very similar to what we had here, right? The C1 was given by this, the C2 or the C0 was given by this. It's the same thing, right? So we have the norm of a vector with itself, and here we have, so we're basically using that projection formula, right? So we're still using that same formula. We're just kind of cutting out the middleman. We're just saying, hey, let's just get straight to what we need, right? And so this is for k larger than 1. bk is the exact same thing, right? Except my function f with whichever sign that it's associated with, right? So a1 has cosine 1x, a2 cosine 2x. So here the k is 2, k is 2, right? So each a sub k that I'm trying to find, I'm using this for the coefficient. For the b's, I'm using this, and for a naught, I'm doing the same thing but with itself, right? So here, notice that cosine is 1 over pi, integral from negative pi to pi of cosine squared, because it's going to be cosine times cosine, right? So using the reduction of power formula from trig, we can replace this with 1/2 times 1, 1/2 times 1 plus cosine of 2, whatever you have inside here, so that turns into 2kx. Here I just multiplied the 1/2 across the identity. So then that helps us to separate this into two separate integrals. The first integral right here, which is 1 over 2 pi times the dx, so that integral. And then here, I'm going to do a u substitution. This is why I put a star. I'm going to reference it down here just in case you're rusty on integration and u subs, because a lot of people forget integration methods because there's so many. It's like the first half of calculus 2. So there's lots to remember. So I'll go over some of those here. But the u sub will be u equals 2kx. So when we make that u sub, we will come out with this integral. Okay. So now when we integrate, we just get 1 over 2 pi x, right? This changes from a cosine to a sine basically, and then the u ends up coming back in, and I get 1 for k pi sine 2kx, and I evaluate that from pi to negative pi, right? Doing so, this will end up falling out because sine of any form of pi, right, any multiple of pi is always 0. So this is just zeros, okay? Here, putting the pi on top will end up canceling it, right? So I'll have a 1/2 minus a negative 1/2, which gives me just a value of 1. So my denominator here is going to be 1 every single time, right? Which is why we did this. So again here, I use the u sub, u was 2kx. I take the derivative of both sides, so I get du equals 2k dx. And then I solve for the dx so that I can substitute dx. 1 over 2k du is dx, apologies. So then when I substitute this in, I'm going to get du times 1 over 2k times the 1 over 2 pi that was already there. So I got the 1 over 2 times 2 is 4, the k, and then the pi that's already there, right? So that's why I had this integral, and I started just as a reference so that you guys can remember how these things work, right? So I'm going to do the same thing for the sine times sine, okay? So for sine inner product sine, same sort of setup. I'm going to use a reduction of power formula as well. I get 1/2 minus 1/2 cosine 2x because the reduction of power formula is 1/2 times 1 minus cosine, and then double whatever you have on the inside, okay? Same thing, I'll separate this into two integrals, okay? So I have 1 over 2 pi x when I integrate this part, and then this turns into a 1/2 sine, right? The signs stay the same for integration from doing a u sub, and I evaluate that from pi to negative pi, which gets me 1 as well because this falls out, it goes to 0, and then I have the exact same situation I had before. So the nice thing is for AK and BK, these are always 1 on the bottom. So really, I just have to find the numerator portions for my AK and BK integration, right? So my AK coefficients are 1 over pi, integral from pi to negative pi, or negative pi to pi I should say, f of x times cosine kx dx, and then my bk's, b sub k's are the same thing, but instead of cosine, sine of kx, right? Now my a naught terms are a little bit different because the basis vector that's there is just a 1. So if I compute those values, right, so 1 inner product 1 is just the integral 1 over pi from pi to negative x, which is x over pi from pi to negative pi, which is 2. Okay, so again, I know I'm going a little fast here, but make sure you pause and you're writing all this down. Checking out your math and arithmetic for yourself on the side would be wonderful. So that's the denominator. So that means that my numerator is going to be the integral of 1 over pi f of x times 1, or just f of x dx. Okay, so for a naught, it's 1 over 2 pi, because remember this is the denominator, negative pi to pi of f of x dx. So all of my coefficients are here. This is how I find my constant. This is how I find each sub k, and this is how I find each bk coefficient. So AK and BK terms, they're called the Fourier coefficients of f. Okay, so now let's do an example, right? So we worked through the formulas that we have. We derived the 3 formulas that we'll be using for these examples. So let's do an actual example. Let's find the Fourier approximation f2 for f of x equals 3 minus 2x. So here, my function every time is going to be 3 minus 2x, and I need to find f2, right? So if you remember what's going on here, I'm finding the nth order Fourier approximation. So I only need to find up to 2. I need a0, a1, a2. I need b1 and b2. So I need those 5 terms. Okay, I need those 5 terms. So there's a couple ways to do this. Okay, one, probably the easiest way, is to find your a0, find a1, find a2, find b1, find b2. So doing that means that you are then computing 5 integrals. Okay, they could be difficult, they could not be difficult. It kind of depends on the function. Okay, generally what we want to do, and a good practice for later courses, is instead of computing 5 integrals, let's do 3 integrals, and let's let those 3 integrals be, one of them be our a0 term, and the other one our generalized ak term and our generalized bk term. That way I can find any value of my approximation, right? If I have my general term for AK and my general form for BK, I can easily compute, let's say, F10 if I have those integrals, right? Once I have the general terms found out, it's easy to find any size Fourier approximation. So we're going to do that just because I'm lazy and it's less integrals. Now the integrals are actually going to be harder because we're going to solve these in a very generalized fashion. But the end result is more usable for me and more beneficial. So you can do it any way you want, honestly, but we're going to do it instead of one at a time. We're going to do the general term, especially since we have a video. I know you guys know how to integrate, so instead of doing the easy peasy ones, we're going to do something that's you can watch over and over again and figure out how to do it in general. Maybe you come back in your PDE class and like, hey, I remember Professor Williams showed me how to do this and it made sense, or maybe you just never use this video after this class ever again. We'll see. Okay, but let's do our examples. So a quick identity here, trig identity that helps, because we're using cosines and sines and we're going to be plugging in positive and negative values in here. These identities help quite a bit. So cosine of negative x is just cosine of x, and sine of negative x is negative sine of x. So this is even and this is an odd function, so that's why it helps. I think earlier in the video I said this was even or I said this was odd and this was even. I don't remember, but this is the property for even functions and this is the property for odd functions. So so that's the correct even and oddness of cosine and sine, which we can also use to figure out when our integrals zero out, right? So remember, if you're taking the integral of something over a symmetric interval, then certain even or oddness will cancel out because you have the positive portion and the negative portion, and they cancel out. So use that fact as well in your integration. So let's go ahead and get started. Okay, so for a0, it's 1 over 2 pi from negative pi to pi of f of x integrated with respect to x. Okay, so this turns into 3x. This turns into 1/2 times x squared times the 2, so that will cancel. And then you have this 1 over 2 pi term on the outside, right? And then we evaluate that from negative pi to pi. So I got the 3/2 pi times x. Here, the 1/2 will cancel with this 2, so I'll be left with x squared times 1/2 pi, right? Evaluated from negative pi to pi. So just plug in our values to see what we get, and we should get out a value of 3. So my constant term is 3. Okay. I would like to find the general form for AK rather than plugging in A1 and then saying, okay, I'm just going to do this whole thing, but this will be just cosine x, and then find A2, where I do it all over again, but instead of 1, I push 2 in here, and then I have to do a U sub and so forth, so which is fine. But let's just do this in general so we can find any kth term. So I can find any size Fourier approximation. I can find the F5 approximation if I wanted to once I have this generalized term. So that's what we're doing, okay? So I'm not going to do this, but it should be very clear here. You would first multiply this out, or at least that's how I would do this. I would turn this into two integrals. That's 3 cosine kx and negative 2x times cosine kx. And that's what I would solve, and that's what I'm doing, although I'm not writing all of that out. That's what's going to happen here, right? So doing that is going to give me, after I do some u subs, right, I am going to get 3 k pi sine kx. That's from having this kx over here and integrating. And then from the negative 2x cosine kx, I'm going to have a few terms, right? So these next few terms come from this integration. So I'm going to get negative 2k pi x sine kx minus 2k squared pi cosine kx evaluated from pi to negative pi. So this comes from integration by parts. I have a nice way of doing integration by parts that I learned that I prefer to use. I definitely do not use the crazy formula that nobody remembers. So I'll show you what's called the Tableau Method. If you have never seen it, it's a very cool method. I remember it to this day, but I have no idea what the actual integration by parts formula is. The one where they have u, gu, v, all these crazy things. I have no idea what that is. So I'll show you another method that's really, really easy to remember. And it's very easy to calculate as well. Okay. So this portion comes from the 3 cosine kx using a u sub and integrating just like we did before. This is from integration by parts. So our final answer comes out to 6 k pi sine k pi. Remember here we're basically treating k as a constant, even though it changes with the different subscript that we're looking at. It's treated as a constant. X is the thing that changes. We're integrating with respect to x, so you treat k as a constant value throughout the integration. So this is our sub. Any a sub k term can be found with this formula, right? So if I want to find the a1 term, I just plug in 1 for k. If I want to find the a2 term, I just plug in 2 for k, right? So it's very, very helpful and useful for me. So note we need to use integration by parts here. So I'm taking not the whole 2, I'm just going to take the x cosine kx portion of it. So the goal is find which one you need to differentiate and which one you need to integrate. Okay. Now if I differentiate x, it will go to 0. If I were to differentiate the cosine x, it repeats. Cosine sine, cosine sine, cosine sine with changing signs, right? So that doesn't help. So the derivative portion is the one you want to go to 0. So I'm going to use x. I'm going to get x, 1, and 0, right? The other function is the one that you're going to integrate. So again, here I'm integrating x times cosine x. This 2 over pi just comes out and I multiply my end result total. Okay. So I'm going to differentiate x until I get to 0. I'm going to integrate cosine x here. As I do so, I'm going to have a multiplier that changes signs starting with plus. So plus, minus, plus, minus, plus, minus, so forth, right? So here, I'm going to do this twice. I'm going to show you how I would do it. First, I would just differentiate the whole row. I can't do a whole row. I have to kind of do one line at a time across horizontally. I can't do vertically. So I'll show you how I do this. First, I would differentiate all of the x's. So I would get x, 1, 0, right? That's the first thing I would do, right? Let's come back. Then after that, I would integrate. Start off with cosine kx. Then I integrate this. I could use a u sub, right? I'm going to end up with 1 over k sine kx. I would integrate this one more time, again using a u sub, so I'll get 1 over k squared, and I'll get a cosine, and I'll end up changing signs. Okay, so I differentiate, I integrate. After that, I put plus, minus, plus, minus, plus, all the way until I'm done. Once I reach 0 here, I'm finished. Now I multiply everything, which is what these arrows are for. X multiplies times this, x sine kx over k, right? And then I multiply this, so 1 times negative k squared cosine kx, and I have a negative and a negative, so that makes it positive, okay? But I'm also negative. I'm also subtracting here. I have a -2 multiplier, so it turns it back negative, right? So this first term was from this first multiplication, okay? The second term is from the second multiplication, and then I have 2, or -2, I should say, over pi times each one, right? That's the integration by parts, the table method. It goes very, very quickly. You can choose to use it all the time or not. I don't really care. It's up to you. But once you're used to this method, it's super fast for integration by parts, and you never have to remember the u, v, dv, du, whatever that is. Okay. So I'm not going to show this again, but that's what I'm doing, right? So you find one to differentiate till it goes to 0, integrate the other one, and then you just from one on top you go down and over, and you multiply those two across, right? You come to the next one, you go down and over, and those are the two. So your multiplication goes across the rows in a diagonal form, right? So hope that was helpful. For bx, I'm going to do the exact same thing. I'm going to do integration by parts again. I'm going to do literally the exact same thing I did before. So here the sine changes to cosine. I have the 3 times, and from the u sub I got the 1 over k. So that's how I got this first 3k pi cosine kx value. And then these next two terms are also from integration by parts, from having x 1 0, and then sine kx 1 over k cosine x, and then 1 over k squared sine x, and alternating signs as well. Evaluate from pi to negative pi will give me this as a result out. Okay, so notice no more x's, just pi's. So whenever I want to find a bk term, I just plug in different values of k, right? b1, b2 is all I need to find for this example, and that's what I'll do. So a1 is going to be 0. Okay, so let's come to our a1. So here, it doesn't matter what value I have of k. I have sine times some constant multiple of pi. This is always going to be 0. My a sub k's are always 0. I'm going to have 0, let's say not 0. I'm going to have no a1, a2 term. Okay, I do have an a naught because it's not multiplied times the cosine, but my a1, a2, a3, a4 whatever, it'll always be 0. Okay. However, I will have these sine terms. Okay. Okay. So a1 is 0, b2 is 0. Here, if I throw in 1, I'm going to have 4 cosine pi, which is just -1, right? And then this is 0. So I have 4 times -1, or -4. And then if I throw in 2, this will be 4 over 2 is 2 cosine 2 pi, which is 1. So I'll just have 2, right? So that's why this is nice, because once you have this form, it's easy. Sine here, this is always going to go to 0. So this is really the only thing that's generating any coefficients for b, right? Now that I have these values, I can just plug them in to my formula, right? I have a naught minus b1 plus b1, so it's a -4 sine x, plus b2 sine 2x. So this is my approximation. Okay, so let's see how closely this fits to 3 minus 2x with a quick abracadabra. Okay, we're in Desmos. So we have our line here, y equals 3 minus 2x. So we're at 3, and then we go 1, 2, minus 1, right? So y-intercept of 3, slope of -2, so that's my line. And I will show you the different Fourier approximations. Okay, so is the F1 approximation. So our F1 would have had just the a naught constant, and then our b1 constant, which was -4, because remember there's no other a sub k's. So this would be, so F1 would be 3 minus 4 sine of x, and that's literally what this graph is, right? I have 3, right? So I'm shifted up 3, and then I have a negative sign. So remember, sine generally goes this way. I have a negative sign, and it goes up by 4, right? So if this is 3, it has a max height of 7 and a minimum height of -1, because it has an amplitude of 4, right? So it does not approximate my line very well, but it does a decent job. So my endpoints here, this is negative pi and this is pi. So over negative pi to pi, it's doing a semi-decent job at whatever this value is, right? So an x value of close to -2 and a positive value of close to -2, it kind of approximates my value. It's semi-close, it's not super far off, right? So if I increase my value by 1, so now this is the F2 approximation, this is our approximation that we made, it's a little bit closer to my line for a bit longer before it kind of strays away and does what sines do, you know, which is start to oscillate. Okay. If I do my F3 approximation, I am much more closer to my line for a lot longer, right? So I have a much closer approximation here. This is the 4th Fourier approximation. This is the 5th, and we'll just play this up until the 20th approximation, right? So again, you can see that I oscillate along my line, and it's a very good approximation. Now, Fourier approximation for a line is never going to be great because you're using an oscillating function to approximate a basically constant function in a sense, right? So if we have a function that has curves like a cubic or some effect like that, our Fourier is going to be a much better tool to approximate a higher degree polynomial or something to that effect. Okay. I guess we can go a little crazy and say, let's go to 100, right? Oh, it only goes to 10 for me. That's fine. It's probably too much calculating. Let's say 30. Right? So that's an approximation of 30. That's the 30th approximation for 3 minus 2x. Okay. So you can see it's very close until you get you have to zoom in very far to start to see the differences in the values. Okay. So that's what Fourier approximations allow us to do. As far as approximating function, Fourier lets us do way more stuff, which we'll get into in just a second. Okay, so we have our F2 approximation here. So what I was saying before, for F1, we would just have the 3 minus 4 sine x, right? And then we kind of saw what happens when we add more and more terms. And again, those are all just generated by the 4 over k cosine kx, because that goes to 0, and all the a k's go to 0 as well, right? So let's move on to our next thing. So if the Fourier coefficients decrease in size at a reasonable rate, we can use the nth order Fourier approximation of Fn as a Fourier series, right? So Fourier series means that f of x is approximately a naught plus the sum of all of those things that we had, which is what we did, right? So if you notice here, these things are decreasing. So as we had lots and lots more, right, when we got to the 30th term, we were pretty much on the line, which is why it says here that our function is approximately equal to this. Obviously, if you go to infinity, right, we went to 30, but if we go on forever and ever, it will equal our line, right? So we take that limit. Okay, so now let's discuss the discrete Fourier transform. So what we were just doing was trying to find an approximation for a continuous function, right? So now this is going to be more aligned with what we were doing in our first example, where we had discrete points, right? There was no function involved. It was just a bunch of points, and we wanted to find a line of best fit. So here we are going to find a sum of sines and cosines in order to try to best fit the data that we can. Okay, and again, the more terms we have, the better fit we'll have. Okay, so here, as I said, just like in the beginning of the section, we may not have a function which we would like to approximate, but instead have a series of data values which we would like to develop an approximation function for, because if we have an approximation function, then we can use it to interpolate or extrapolate data, right? A discrete Fourier transform is very good at creating a function, a continuous function, one that's infinitely differentiable and infinitely integrable, right, which is important for us when we have functions, that can approximate our data points. And again, the more terms we have, the better that function is at approximating our data. Okay, so say all of our m points, so let's say we have m of them, is equally distributed over the interval negative pi to pi. Now, of course, this interval is important because that's the interval of our continuous functions that we're looking at for our inner product space, right? Then the change in x for each of these inputs is going to be 2 pi over m, which is the number of data for each x sub I that we have. Now, hopefully this is looking familiar to you because we're we are basically going to set up a Riemann sum, right, which will basically look like this. Okay, so remember, a Riemann sum was the way that we approximated the area under a curve, but we're going to do that now in order to find a function of best fit. Okay, so let's say g is this unknown function that we have, right? So we have data values and we want to be able to approximate it. So let's say g would have been that function. Okay, then 1 over pi integrated from negative pi to pi of g of x d of x, okay, is going to equal or be approximately equal to this Riemann sum that we're going to find that we extend from negative pi to pi, right? So we're going to have the 1 over pi constant that's still there. We multiply always, so just go back to thinking about rectangles under the graph, right? So all of their widths will be delta x. Delta x is 2 pi over m. And then we'll multiply all of those rectangles by their height, right? So it's a bunch of areas. They have equal widths, which is why we pull this out as a constant. And their heights are given by g evaluated at each of those x sub i's, right? Or in the first case, 2 pi m minus pi, right? So 2 pi m minus pi will give you the first value. It will not be negative pi. It'll be the first x value after negative pi, right? That is 2 pi m away from negative pi. I want to go another 2 pi m away to get to the next data value, and that will be 4 pi m minus pi. Okay, I want to go another 2 pi m away from negative pi, and so forth and so forth and so forth until I get to pi. So here, notice that m over m will give me 2 pi. 2 pi minus pi will be pi. So this last data value, or evaluated at g, is g evaluated at pi. So what this will give me when I simplify everything is the pi's cancel. I got 2 over m, and I'm getting the sum m terms, okay, up to m, starting from 1, okay, so here I'm starting at 1, of 2j pi over m minus pi. So this is what we would consider as the right-hand approximation, right, for the function g of x, for the area under g of x, okay. So that's an approximation to this integral. Okay. For our Fourier function f, we can approximate the Fourier coefficients with the same formula as before. So we're going to use the same thing with the integrals, but instead of integrals, we're going to use our summations, because integrals are basically summations, right? Summations that go to infinity. So my c naught, instead of being 1 over 2 pi integral of etc., we're going to have just we're going to change up this a little bit, right? So before it was 2 over m, so when I had a naught is 1 over 2 pi. So since my function is different, it was 2 over m, I basically have the same thing. So it'll be 2 over the here it'll cancel out, and it'll give me 1 over m instead. Okay, so it's very, very close in formula. So we're using this, and we're basically applying the other formulas that we had, right? So here the 2 will cancel out, and we'll have the m. The m is acting like our pi, right? And then we're going to evaluate at my function value f that we're using to approximate g. Okay, so the same function, but at f instead of g, because I don't know what g is, but I'm making a Fourier function approximation. ck will be very, very similar. It'll be the 2 over m, right? Because before we had 1 over pi, right? So my function here, again, is 2m, so that's like the 1 over pi value that we had. So that stays as 2m. F of this value that I have times cosine evaluated at the same points, right? But instead of at pi, it has to be at k pi because that's what we had for the bases for that function space, right? Instead of bk, we're going to have dk, and it's the same thing. 2 over m, the summation up to m, f evaluated at those same points, and then sine at the same points as the cosine, because it has the k pi instead of regular pi here, and has the k here as well because it needs to be k times this value, so the k gets distributed across for both of these. So it's really the same thing, it's just that we're doing this like we're doing a Riemann sum instead. So regardless if you understand how these are derived or not, these are the functions that we're going to use. Obviously I'm going to use them so you're familiar with how these work, but it's pretty straightforward. You're just plugging in these values, okay? So let's go ahead and go. So the nth order discrete Fourier approximation is defined by Gn of x being c0, okay, plus c1 cosine x, c2 cosine 2x, so forth and so forth, till you get to cn cosine nx, d1 sine x, d2 sine 2x, so forth and so forth, to dn sine nx. So very, very similar to the last formula, except that they're found using summations instead of that inner product. Okay, so again, here we are using Gn instead of Fn because Fn is reserved for the Fourier approximation. So I wouldn't say, hey, we need to find F sub n and be referring to the discrete Fourier approximation when we are already saying Fn is the Fourier approximation for the continuous function, right? So when you see the G sub n, we're talking about discrete Fourier, right? When you see the Fn, we're using that integral formula with the inner product space. Okay. Well, this is inner product space as well, but the defined inner product of the integral from negative pi to pi of f of x times g of x. Right. So again, Gn of x is the discrete Fourier approximation. Right. So let's go ahead and start our example. This is our last example. So lucky us, right? We're kind of long here. For this video, let's find the discrete Fourier approximation, G2, for f of x based on the table of values that are provided. So this is x, and this is the f of x, right? So these are just points in space. Negative pi 2, negative 2, 0, negative 1 is a point, pi over 2, 0 is a point, and pi and 2 are points as well. So these are inputs, and these are output values, obviously. Okay, so here m is 4, we have 4 points. Here n is 2 because it wants us to do the second discrete Fourier approximation, so n is 2. And now we're just going to plug our stuff in. So I'm literally just plugging this into my formula. So I have 1 over 4, right, 1 over m. I'm going up to the mth term, the 4th term. I'm going through each data value here. And then it's f of, again, 2 j pi over m, right? So that's 2 over 4. So that's why this turns into 1/2. There's no k's here for the c0 term. I'm just going straight to this formula. So my first term is I am plugging in 1/2 times 1 times pi. So 1/2 minus pi is negative pi over 2, right? So 1/4 times f of negative pi over 2. The next term is 2 over 2, right, because j is 2, so that's pi minus pi, or 0. So plus f of 0. Then the next term is, 3 over 2 minus pi, so that leaves me with the pi over 2. And then the last term will be the pi, right? All I'm going to do is substitute these values. So the first one's always easy. It's literally each of the values that should be given to you. So this is just 1/4 times negative 2 plus negative 1 plus 0 plus 2, right? Oops. Which should give me negative 1/4, and you can calculate that yourself if you're not sure that that's what you get. But here you get negative 2 times 2 is 0, plus 0 will leave you with negative 1. Negative 1 times 1/4, negative 1/4, right? C1 is going to be the same thing, okay? This formula remains unchanged. I will always be plugging in each of the values that they're giving me. However, this cosine is unique because k in this case is 1. So it mirrors the exact function I have already, which is nice because that means I'll do not 1/4 but 2/4 or 1/2 times f of negative pi over 2 times cosine negative pi over 2 plus f of 0 plus cosine of 0, because these indice functions are identical, right? Telling me which values I need to plug in. They're identical because it's at k is 1, so it's the same thing. So it's nice because they're identical, right? So I'm going to get 1/2 because 2/4 is 1/2 times f of negative pi over 2 cosine negative pi over 2, f of 0 cosine 0, f pi over 2 cosine pi over 2, f of pi cosine pi. So I'm just throwing these values in, right? So that's negative 1/2 times negative 2, this is 0, right? Times negative 1, cosine of 0 is 1. Okay, both of these are 0. F of pi is 2. Cosine of pi is negative 1. So now I'm just going to calculate these values. It's 1/2 times 0 times 0, negative 1, negative 2. So that's a negative 3/2. Okay, so again, once you understand, you're just plugging these values. The only things you actually have to calculate here are these cosine values. Okay, I just not gotta draw yourself a graph of cosine, and it's much easier to find these values if you don't remember them off the top of your head. Okay, so now we're going to move on to, we want G2, so I'm going to need C2 as well, right? So C2 is a little different. I still have the 1/2. The F's are the same. This is going to be different, right? Because now it's 2jk pi over m. So here, k is 2, so I have 4 on top. M is 4, so that ends up canceling. So I just have j pi minus k pi. Here k is 2, right? So j pi minus 2 pi. So now, again, my f values are going to be identical to what they were in both cases here, right? For C1 and C0, but my cosine values will be slightly different. So make sure you don't just go all willy-nilly and start trying to do stuff, right? Oops. I don't know why this equal sign is off, but that's whatever. I'll fix that later. I'll have 1/2 times, again, f of negative pi. Here, pi minus 2 pi is cosine negative pi, right? My next j is 2, so 2 pi minus 2 pi. My next j is 3, so that's 3 pi minus 2 pi. And for the last one, that's 4 pi minus 2 pi, or cosine 2 pi. But the f of pi, f pi over 2, f of 0, f negative 2 pi, we have all those values. They are not changing for me, so that's nice, right? So I get 1/2 times, and then I'm just plugging in all of my values, right? Positive 2, negative 1, positive 2. So this will be 3/2, okay? And then I need to do the same thing that I did for the D's. Okay, here again, my K is 1, so my indices for sine are going to be identical to F, so that makes it very easy. It'll be F negative pi over 2 sine negative pi over 2. F of 0, sine of 0, right? F of pi over 2, sine of pi over 2, because the inside index for the inputs are identical, right? So again, I get 1/2, and that's because it was 2 over m, and my m is 4, so that reduces to 1/2. So going through this, it's going to look just like I said before, right? The inputs for f and the inputs for sine are identical. So as long as you know these values, right? Sine of 0 is 0, sine of pi is 0, this will be 1, this will be negative 1. So that makes it easy to know what I'm plugging in, and we calculate our values and get 1, right? This is positive 2, 0, 0, 0. So it's just 2/2, which is 1. I do the same thing for D2, but notice my indices for the sine here in D2 is going to match what I had here. So that's nice as well, because now I can just copy the cosine and sine here, not the values, but the inputs. So this will be 1/2 f of negative pi over 2. Instead of cosine, it'll be sine negative pi, right? So it's going to follow this exact formula. Instead of cosine everywhere though, it'll be sine. So there's a lot of symmetry that goes on between the C's and the D's. You just got to make sure you swap out your functions. You're not just copying the output values, right? You got to swap the functions and figure out what those are going to be. Okay, sine 2 pi, cosine 2 pi, sine pi, cosine pi. But the f's are all the same, right? So I got negative 1/2. I know all these f values. So here now we have sines of pi's, right? Negative pi, 0, pi, 2 pi. Those are all 0. Okay, everything here is going to be 0. So I don't have a d2. Okay, and now I just put all my coefficients together. I put this d1, this c2, and this c1 and this c0 that I have. I put all those together into my formula here, okay, for G2. So I only have to go up to the second term on each one. Okay, oops. All right, so G2 is negative 1/4, right? So that's C0, C1, C2. D1 was 1, there was no D2, and I'm just throwing them with their cosine or sine functions. And the graph of this looks like that, right? So these are my points, and then my function oscillates between it. But notice again, what we're trying to do is not necessarily just hit the points, but we're trying to minimize the distance from the points. Okay, so my function and the distance between them, as far as sums of sines and cosines, should have minimal distance differences. Okay, now if I had a larger approximation like G10 for instance, it's very possible that it hits all these functions and it does a good job of staying in a curved line to fit the data points. Okay, so again, it really just matters on what your approximation number is here. Okay, hope this wasn't too crazy for you guys. I will see you on the next video.